Hello everybody, Math Hobo here, and today we are going to be talking about moment of inertia and rotational kinetic energy. So let's begin. Moment So what is moment of inertia? To discuss that, we will need to first discuss what is rotational kinetic energy. So before we discuss that, let's discuss what linear kinetic energy is. So many of you have seen this before, and I won't go into explaining this because it can be found in practically every physics textbook. But KE linear, so the linear kinetic energy is determined by the equation KE is equal to half mv squared. And that's for when you have a particle and it's moving with some velocity and it has some mass m, then it has kinetic energy at this point in time. It has kinetic energy 1/2 mv squared. But now let's ask the question. Let's say that instead of it being it moving in linear motion, let's have it move in circular motion. So let's draw the circular path. It's this as mass m, and it's moving in a circular path fixed around some center C, and it has some radius r. So then if we would like to determine the rotational kinetic energy of this system at this point in time, we'll need to determine well, what is its tangential velocity v. And we know that that if we have this and if we have some distance s, then some radius r and some angle theta, and this theta must be in radians, then this s is equal to r theta. And then, since we want to find velocity, all we must do is take derivatives on both sides, and we have ds by dt, which is the same as velocity in this case, is equal to r, since r is simply a constant, r d theta by dt. And what is d theta by dt? In physics, we like to call that omega. So d theta by dt is equal to omega. And let's not confuse that with the omega found in spring equations and wave equations, because that's a completely different thing altogether. So now we have ds over dt is equal to r times d theta over dt. Now ds over dt is equal to v, and d theta over dt, as we confirmed over here, is equal to omega. So now we have v is equal to r omega. And let's rewrite that. So we know now that v is equal to r omega. And just a clarification, this d theta by dt, sometimes in physics it's also written with Newton dot notation. So it's theta dot, and that's the number of dots represent how many time derivatives you take. So for example, theta dot dot would be the second derivative of theta with respect to time, and this would be d omega by dt, and this would also equal alpha, which is angular acceleration. So this is simply angle, the angle, and this is angular velocity, and alpha is angular acceleration. So now that that's clarified, let's move on. So we know that v is equal to r omega, so we can take linear kinetic energy and simply substitute our equation for v into half mv squared. So now we have half mv squared, that's going to be half m times r omega whole squared, so we have half m times r omega whole squared, which is equal to half m r squared omega squared. I should be using capital R's. Yes. Wonderful. So now we have come up with an equation for the rotational kinetic energy. And now, since physicists are extremely complicated and like using simpler symbols to denote very complex expressions, we're going to call this term half mr squared. We're going to call this term I. So then, this is just a change. We're just calling this term I. Then the rotational kinetic energy, or Ke rot, is equal to half I omega squared, because you have I times omega squared times half. So wonderful. Now this is the equation for rotational kinetic energy that we are so familiar with due to our friendly physics textbooks, and we will be discussing exactly what this term I is. Now recall that I was equal to mr squared. Now let me ask you, what is r? And I'm going to erase all of this here for just a second. So what is r? And since we're dealing with rotations, we're dealing with, in essence, circular motion, and r is simply the radius, which is associated with that circular motion. So let's erase this picture here for a second. So when we discuss the kinetic energy of a rotating body, we use this equation. Now, what sort of rotating body do we use? We use something called a rigid body. And in physics textbooks, that's usually drawn like some squiggly shape. But all you need to know is that this shape is rigid in that as it's rotating, different components do not rotate at different angular velocities. So when it's rotating, when this entire thing is rotating about the center of mass with some angular velocity omega, then every component in the system, every single tiny infinitesimal portion that constitutes this entire system, this entire rigid body, is moving with the same exact angular velocity omega. Now they will be moving with different linear velocities because omega is equal to v by r. So, and r will differ because this r is not the same as that r, is not the same as that r. So it's intuitive that the linear velocities will differ, but the angular velocities will stay the same for a rigid body. So now let's discuss, if we have a rigid body, and we have this concept of kinetic energy, rotational kinetic energy, then what exactly is our I? A useful thing to note here is that the moment of inertia I is purely dependent on the shape and the size and the shape and the configuration of the rigid body in question. So let's draw a two-dimensional rigid body, and let's have an axis going through the center of mass. Let's have that right here. This is center of mass, and let's have an axis going through that perpendicular to the plane of the rigid body, and that is going to be our axis of rotation for this rigid body. And now let's say that we have some d, some tiny infinitesimal section of this rigid body, which has mass dm. Now the question is, as the body rotates, because we are dealing with rotational kinetic energy, as the rigid body rotates, how does the specific section dm rotate? Well, dm rotates in circular motion around this center of mass right here, and it rotates with radius r. And we're getting a little bit scrunched up in our room here, so let's title this RCM. So we have some radius associated between the center of mass and the infinitesimal section which we are observing as it goes through circular motion. So now that we have the mass in question and the radius in question, we can evaluate effectively mr squared. So the moment of inertia I is equal to mr squared. So the moment of inertia I for this tiny section dn is equal to r squared cm times dn. And I just substituted in dm for m and rcm for r squared, and rcm for r. So now we have some notion of infinitesimal moment of inertia. We should actually write this as di. And what we would like to do is we would like to find the total. We would like to find the total moment of inertia. So we would like to take into account every single dm which constitutes this entire rigid body. And that would mean taking into account the radii and the mass for different parts, for different sections, for different regions of this rigid body. And one thing that we must note now, it's a little bit late to note, but we must note that the mass is, well, let's not write it here. Let's write it up here. So, I just rewrote that because I erased it, but what I wanted to write was that mass is distributed evenly throughout the rigid body. And this is very important because if mass was not distributed evenly, and we had different masses and we had different densities throughout this rigid body, then it would be much harder to evaluate the total moment of inertia. So we would like to assume that our rigid body has even mass distribution. So we can proceed from there by trying to take the total moment of inertia for this entire rigid body. And we clarified what that means. That means considering different dm's that constitute this entire rigid body. So what we must do is we must evaluate this function and at each dm, and then we must sum up this function evaluated at each dm for all the dm. And what does this look like? This looks like the I total, or the moment of inertia of the entire rigid body, is equal to the sum over I of each respective radius. Let's not write RCM anymore, let's just stick to RI, because that's more concise. So each Ri, so this guy would have, this dm would have Ri, and this dm would have Ri, and different values, or this guy would have Rj. You get the concept. They have differing values of R, so we sum up over different values of Ri times different values of dm. So the this squared. So we evaluate the function and we sum it over each different dm. And since we have a sum, an infinite sum, because we have infinitesimal dm parts in our rigid body, we have the infinite sum of r squared, rri squared times dmi. So that becomes an integral. And this is actually easier to see using this equation that we wrote here, di is equal to r squared cm dm. So all we must do is take integrals on both sides of both of these equations, and let's actually erase our picture here. So if we integrate both sides, then for this side we have integral di is equal to integral r squared cm dm. And let's just abbreviate this to r squared. So it becomes integral r squared dm. And this side we have integral, or we have I total is equal to, and the sum of infinitesimal parts becomes an integral. Integral r squared dm. And then it's important to know where we're integrating. We're integrating over the entire rigid body, so let's abbreviate that to, actually no, that's bad. We have two r's. Let's just say region. Region. Wonderful. Now we have come up with a concise definition via the integral of what our total moment of inertia for a specific rigid body is. And oh, we forgot to simplify this. The integral of di is simply I, so we get the same exact definition from both ways of looking at it. So this concludes our section on finding the moment of inertia, the total moment of inertia of a rigid body. Thank you very much.